morning, respected teachers and my dear friends. On this day dedicating to mathematics, we ourselves, Hari, Keshav, Vishal and Alan are here to fill your brains with the amazing fractals in nature. I hope you would enjoy and learn at the same time. Let's get going with the video without much delay.
Mathematics in nature. Mathematics is visible everywhere in nature, even where we are not expecting it. It can help explain the way how galaxies are spiral, as seashell curves, patterns replicate, and rivers bend. Mathematics makes our life orderly and prevents chaos. Here are some of the best examples of fractals seen in nature. Wait a minute, we can't start without an explanation of what fractals are.
So, what exactly are fractals? A fractal is a never-ending pattern consisting of infinitely complex patterns that are self-similar across different scales. In simple words, if you divide a fractal pattern into parts, you get a nearly identical reduced size copy of the whole. Well then, sit back and enjoy this collection of 10 marvelous display of fractals put forward by Mother Nature with utmost complexity, many of which you have not heard of.
Snowflakes. How can snowflakes be fractals? In the case of snowflakes, the starting point of the fractal is in the center and the shape expands outward in all directions. As the crystal expands, the fractal structures are formed in each direction. Each iteration of the shape gets smaller and more detailed, which also contributes to the overall complexity of the shape.
Lightning. Lightning is one of nature's most powerful displays of fractals. As current passes through the air, it becomes superheated. Superheating of air changes its electrical conductivity and allows the current to fragment out. This process repeats itself for each level of fragmentation and soon you get a fractal. It is considered a fractal because the main beam of lightning is branched and it goes on.
Human respiratory and circulatory systems. If you take the human respiratory system, you will see a fractal that begins with a trachea, also called windpipe, which branches into two bronchi, which in turn branches into numerous bronchioles and expands into a much more fine-grained network of cavities. Similarly, in the human circulatory system, the oxygen-carrying major arteries emerging from the heart branched into comparatively smaller ones, which in turn branches into tinier arterioles and finally into very fine capillaries. All of these are great examples of fractals in the human body.
Nautilus Shell. Nautilus shells are made by a marine animal called the nautilus, which belongs to the phylum Mollusca. Nautilus shells are also brilliant examples of Mother Nature showing off her geometry skills. Each chamber is a smaller iteration of the one that precedes it. This special pattern it follows is also called the Fibonacci spiral. Doesn't it seem like the James Bond intro is at the end of the Nautilus shell?
Romanesco Broccoli. How can it be a fractal? A small piece of Romanesco Broccoli, when viewed up close, looks the same as a large chunk. This proves its fractal nature.
Air bubbles. When a foam forms, there may be some number of large bubbles interspersed with smaller ones in the gaps, which in turn have even smaller bubbles in their gaps and so on. The bubbles are approximately self-similar on smaller and smaller scales and hence being a fractal.
Fractals found in leaf veins. This main vein passing through the center of the leaf repeats itself within a branch into another branch and into further smaller minute branches. This therefore makes it a fractal.
Rivers. Well, let's now take a look at the fractal branching patterns of river delta ecosystems. Due to erosion caused by various natural phenomena, the main course of the river starts to spread out into various distributaries, which in turn branches into smaller streams. The tiny, bendy streams are just smaller versions of their bigger relatives.
Angelica Flowerhead. What is an Angelica Flowerhead? Angelica is a flowering plant native to Sierra Nevada. The flowering head is roughly spherical. Each part is similar to the whole head, having a stalk and its own sphere of flowers. This makes it a fractal.
Succulents, spiral aloe. Any plant with thick fleshy tissues adapted to water storage is called a succulent. Here we take the example of leaves of spiral aloe. Spiral aloe leaves are a great example of fractal spirals of Fibonacci spirals. They make never-ending patterns formed by the repetition of a single shape. If you divide the same into parts, you get a nearly identical, reduced size copy of the whole.
I have a question. Is onion a fractal in nature?
Onions are not fractals as they do not contain a minimum of two matching or similar regions in which the arrangement of elements are either mirrors or imitate the structure of the object as a whole.
Are peacock feathers fractals?
The inner layers of the peacock feather are not continuous, as the patterns do not match to that when it is seen as a whole.
Oh, then are roses fractals?
Yes, roses are. The reason is that the numerous small petals extending inwards look like the flowers as seen as a whole. How to make a fractal in Microsoft Teams?
First of all, open Microsoft Teams, start a meeting, and invite your friend to that meeting. Then, join the same meeting through another device without leaving the meeting from the first device. You can also join the meeting through Google Chrome. Next, share your screen in one device. Next, look at the meeting window of your other device. Now you can see the fractal you made through Microsoft Teams. For more effect, you can move your cursor around or ask your friend to react.
Thank you.
My dear friends, today in this special occasion, I'll be explaining about the golden rectangle. The golden rectangle is also otherwise known as the golden ratio, and it's also otherwise called as the mean ratio or the divine ratio. A quantities or the ratio is said to be in the golden ratio when the ratio of these quantities is same as that of the sum of the larger of the two quantities. For example, if we take A and B, and if we take A as the larger quantity and B as the smaller quantity, the formula will be A plus B by A is equal to A by B. The Greek letter phi is denoted for the golden ratio. The golden ratio is approximately 1.618. Now, one of the applications of the golden ratio being the golden rectangle. The golden ratio can be applied on golden triangles, pentagons, and pentatrigonometry. The golden rectangle is a kind of rectangle which has a side length of the golden ratio, and it should be in 1.618 ratio. It can be otherwise said as 1:1 plus root 5 by 2 or 1:phi. The golden rectangle is mostly used in aesthetic purposes such as in architecture, art, and sculpture, and it is also found often in nature. Now we'll be talking about golden rectangle in nature.
Golden rectangles found almost everywhere in nature, from the flowers to the galaxies, even from the tiniest arms of the human, as well as from the ears, eyes, nose, almost all the facial regions, as per Leonardo da Vinci. Golden rectangle can also be used to describe the various mysteries in nature which cannot be explained using the human mind. Now, one such example in golden ratio in nature is the golden rectangle in the snail shell. Now, we have seen the snail shell. It is like a spiralized form of shell. The spiral is exactly that of the spiral formed in the golden rectangle. Upon observing the shell well, we can observe that the golden spiral or the spiral formed into the golden rectangle is formed. Hence, the snail shell is one of the examples of golden rectangle in nature. Golden rectangle in the sunflowers. Now, we always pondered upon why these ones, how can we recognize the directions of the spirals in the sunflower? It can be explained using the golden spiral of the golden rectangle. The sunflower has a spiral formation which causes an illusion in the eye. To describe this, we have the golden rectangle. The golden rectangle can separate out the individual spirals caused due to the seeds of the ray florets of the sunflower. Hence, another example for the golden rectangle. Now, another example is the golden rectangle in galaxies. Now, sometimes we look at our Milky Way in photographs and we wonder how can we define it as a spiral, or there are other galaxies which have the spiral. Well, for a fun fact, these galaxies too are aligned in the golden rectangle. The spiral formed in our own Milky Way is formed due to the golden rectangle spiral formed due to the golden rectangle each. Thank you.
Have you ever thought about how nature likes to arrange itself in patterns in order to act efficiently? Nothing in nature happens without a reason. All of these patterns have an important reason to exist, and they also happen to be beautiful to watch. Mathematics form the building blocks of the natural world and can be seen in stunning ways.
Hexagons in nature. Honeycomb. A regular hexagon has 6 sides of equal length, and this shape is seen again and again in the world around us. The mathematician Thomas Hales proved the honeycomb conjecture in 1999. Bees build their hive using a tessellation of hexagons.
Tessellations are geometric patterns that repeat with no overlaps or gaps. Shapes such as triangles, squares, and hexagons can tessellate. You can point out the repeating pattern of tessellations in the fabric of quilts and tessellating patterns on many items, from soccer balls and checkerboards to floor and ceiling tiles and the brick walls.
Foams or bubbles. This is one of the fundamental patterns in the natural world. It focuses on the structure of foam and how it can be found in the structure of a wine cork to the froth on a cappuccino. We also see hexagons in the bubbles that make up a raft bubble. Although we usually think of bubbles as round, when many bubbles get pushed together on the surface of water, they take the shape of hexagons.
A spiral is a curved pattern that focuses on a center point and a series of circular shapes that revolve around it. Examples of spirals are pine cones, pineapples, and hurricanes. The reason for why plants use a spiral form is because they are constantly trying to grow but stay secure. A spiral shape causes plants to condensate themselves and not take up space, causing it to be stronger and more durable against the elements.
Fractals. A fractal is a detailed pattern that looks similar at any scale and repeats itself over time. A fractal's pattern gets more complex as you observe it at larger scales. The same basic shape is seen again and again in the shape itself.
Another common shape in nature is set of concentric circles. Concentric means the circles all share the same center but have different radii. This means the circles are all different shapes but one inside each other.
Have you encountered a maths problem where at first everything seemed easy to do and understand, but then when you go deeper into the problem, you understand that, well, it's not so easy anymore. Yeah. Hi guys, my name is Gopal and I'm from class 11 Silver Oak. I'm here to tell you something about a very special problem. It's called the Collatz conjecture. Okay, let's take a number, a natural number, and apply two rules to it. The first rule is, if it's an even number, you divide that number by 2. Well, if it is odd, you take that number, multiply it by 3 and then add 1 to it. Simple enough. So, pick a number. 3. Good choice. So here I have the diagram of how these two rules apply to the number 3. First, it's 3. Yeah, it's odd. You take the number, multiply it with 3, add 1, you get 10. 10 is even, divided by 2, 5. 5 is again odd. Into 3 plus 1, you get 16. Now 16 is even, you get 8. 8 is even again, you get 4. 4 is even again, you get 2. And 2 is even and you get 1. Now you get 1. 1 is odd, right? So 3 into 1 plus 1 is 4. 4 is even, divided by 2, 2. 2 is again even, divided by 2, 1. Yeah, we're in a loop here. So basically this is the Collatz conjecture, where the famous mathematician Lothar Collatz said that every positive natural number will always end up in these 4 to 1 loop if you apply these two rules given here. Great. So has this conjecture been proven or true or false? No, neither. This conjecture has held true for 2 to the power 68th number. That is huge. It's almost 3 followed by 20 zeros. Yeah, that huge. With the help of supercomputers, of course, not by brute force or of mathematicians, obviously. So, how can we prove this to be true? Take a look at this. This is a directed graph, something that looks like a tree of sorts. As you can see, every number threads down to this one main trunk, which is the powers of 2. Now, if you were able to somehow prove that one of these numbers were to shoot off to infinity, that is, it does not obey the same gravity that other numbers seem to have, well, you have just proven the conjecture false. But then, if you are able to show somehow by algebraic and other alphanumeric methods that this number, every number, ends in this 4 to 1 loop, well, you prove the conjecture true, right? Famous mathematician Paul Eroder said that mathematics was not yet ripe enough for this problem. Well, can you be the mathematician that can solve this and crack the code? Happy National Maths Day.
Thank you.